In the last 3 sessions, 2 of them, 22 and 21, were on problem solving on the topics of Fourier transform, discrete Fourier transform and Z transforms. And the previous lecture, lecture 20, was concerned with DSP, digital processing of analog signals. In particular, we examined the sampling theorem very closely and also made some comments about band pass sampling. Band pass sampling requires a minimum sampling frequency equal to twice the bandwidth, not twice the highest frequency, and that makes life comfortable. The motivation for analog filter design are twofold. One is that in digital processing of analog signals, we do require low pass filters at the front end and also at the reception end. At the front end to constrain the bandwidth so that the requirements of the sampling theorem are satisfied, and at the far end to get rid of high frequencies from the digital to analog converter. Okay, that's the first motivation. Second motivation is that our IIR design, one of the most important and useful in practice, IIR filter design is based on analog filter. Is based on analog filter design using a transformation from S plane to Z plane. S to Z, we use a transformation. We first, the procedure is like this. In the first step, we get the specifications of IIR filter. This will be in terms of, you have to convert this into digital normalized frequency specs. You convert them to an analog filter design specs, design the analog filter, and then go back to the Z plane through the S to Z transformation. So, the motivation for analog filter design discussion in a DSP course are twofold. One is we do require analog filters, and second, our DF design, a major part of DF design is based on transformation of analog filters. It also is a fact that a discussion of low pass filters is adequate because any low pass filter can be converted to any other kind of filter. And as far as low pass filters are concerned, we shall concentrate on 2 types, namely Butterworth and Chebyshev. Because in most of the practical cases, these 2 types suffice. The most optimum filter is of course the elliptic filter, but the problem in elliptic filter is that the design requires numerical computation in almost every case. It is very difficult to tabulate elliptic filters, and no elegant mathematical formulas are available, and therefore in most cases digital signal processing engineers appeal either to the Butterworth or to the Chebyshev. Butterworth is the simplest, but it may involve a little more cost than a Chebyshev filter. We shall discuss both of them. In LPF filter, we also concentrate on only one kind of filter, the so-called all pole filters, all pole LPF. That means the filter only has poles in the finite region of the S plane. Now, there cannot be a filter without zeros. The number of zeros and number of poles should be the same for any transfer function. So, there are zeros, but these zeros are all at infinity. And now we shall consider H A of S, because we are considering analog filters, and therefore all pole low pass would be some constant divided by S to the n plus A n minus 1, S to the n minus 1, and so on and so forth, plus A1 S plus A0. In deviation from digital filter transfer functions, in digital filter transfer function we always write the constant term as unity. Here we shall write the coefficient of the highest power as unity, because we shall write the poles as S minus Pi continued product, so that the highest power has a coefficient of 1. Therefore, the lowest power, the constant term, shall be simply the product of P sub i's with signs appropriately taken care of. If we take this as S plus Pi, then A0 will be the continued product of P sub i's. Okay. A1 similarly shall be, what shall be A1? What shall be A n minus 1? Sum of all the pairs. Okay. So you can find that out. Our aim therefore is to find an H A of S, which is some constant A divided by D of S, with D of S of the form S to the n plus A n minus 1, S to the n minus 1, and so on, in such a manner that the given specifications are satisfied. Okay. Given specifications for a low pass filter are typically the magnitude is normalized to 1. Typically it would be of this form, that is a pass band is specified 0 to omega p. We use capital omega for analog radian frequency, analog angular frequency. The stop band omega s, the beginning of the stop band is omega s. The difference between omega p and omega s is the transition band. Then there is a tolerance, let us say delta 1, delta p. This is 1 minus delta p in the pass band, and there is a tolerance delta s in the stop band. All right. So typically what will be specified is omega p, omega s, delta p, and delta s. From these 4 specifications you shall have to determine an H A of S which satisfies these specifications. Okay. This satisfaction of specifications also has to be explained. You may not be able to exactly satisfy the specifications. Okay. And you can take liberties with the stop band, but not with the pass band. Many of the textbooks say to the contrary, but the practical design experience is that if you take liberties with the pass band, you spend more man hours. Engineer, I am saying man in a global context, man and woman are both man. They spend more engineer hours in designing the filter. The pass band is sacred. The stop band you can take liberties. Liberties means what? You can over satisfy. For example, if my stop band starts earlier, I am happy. Isn't that right? Because I over satisfy the stop band. So this is what our job is, to determine an H A of S which satisfies these specs. And to this end, the Butterworth filter simply takes H A of j omega magnitude squared as equal to 1 by 1 plus omega divided by omega c to the power 2n. Nth order Butterworth filter has a magnitude squared function equal to this. And you notice that at omega equal to omega c, magnitude H A squared is equal to half irrespective of the order n. and wherever the magnitude squared is half is the frequency at which 3 dB attenuation occurs, and therefore omega c is called the 3 dB bandwidth of the Butterworth filter. Okay. You also notice that the magnitude squared, if we plot it versus omega, it goes down monotonically. There are no maxima or minima, and therefore if we plot h sub a j omega magnitude squared, let us say, or let us plot the magnitude, then the ideal is this 1 and the value at omega c shall be equal to 1 over root 2 irrespective of the value of n, and therefore if we plot for various values of n, we will get plots like this. Where capital N is increasing in this direction. That is, as you increase the order of the filter, all of them have the same originating point, omega equal to 0, and the value is 1, all right, and the same end of the pass band. We are calling the pass band as the 3 dB as the 3 dB frequency, omega sub c. So all of them meet at omega c, the value being 1 by root 2, all of them meet at omega equal to 0, and if that occurs, then obviously the error defined as 1 minus magnitude a h a of j omega, that decreases as the order increases, all right. The error, by error we mean error in the pass band as well as the stop band. You see the blue curve has a higher cutoff slope, and therefore its omega s, the edge of the stop band, starts much earlier than the other curve, for example the brown curve. Okay. So what you do is you determine the order n required for meeting the given specifications, all right. And if omega sub c is known, then that's all that you have to determine. If omega c is known, then all you have to do is to find the order that is required to satisfy the given specifications. You should not over satisfy the specs by choosing a higher order. You should choose only the minimum possible order, because if you make a mass manufacture, as most of the industries do, every increase in order requires a few dollars more, and therefore if you make 1 million of them, the company has to incur a lot of loss. The companies usually industry usually sticks to the minimum possible. How much less can I spend to be able to earn how much more? Okay? So that is what they You also notice that this monotonicity h a of j omega magnitude can be written as 1 plus omega by omega c to the power 2n raised to the power minus half. And if you expand this, then you get 1 minus half omega by omega c to the power 2n plus higher powers. The next will be omega by omega c to the power 4n, all right, squared of this is 1 plus x to the power minus half is 1 minus half x plus 3/8 x squared, and so on and so forth. So higher powers of omega by omega c to the power 2n. And you see that if you differentiate the magnitude with respect to omega and put omega equal to 0, If you differentiate, differentiation of 1 is 0. So, you shall get omega 1 by omega c to the power 2n multiplied by omega to the power 2n minus 1, and if you put omega equal to 0, obviously this will be equal to 0. The next differential coefficient shall also be equal to 0, and this will continue up to the ith differential coefficient, where I goes from 1 to how many such differential coefficients shall vanish at the origin? Twice n minus 1. If you differentiate x squared, all right, the first differential coefficient is twice x, second one is, so twice n minus 1 differential coefficients shall vanish at the origin. The twice nth differentiation will give you a constant, right, and therefore you cannot think of any other function which will have twice n minus 1 differentiations vanishing at omega equal to 0. If one differential coefficient vanishes for a function at a particular point, we say the function is flat at that point. It has either a maximum or a minimum, and we say that the function is flat at this point. This function, Butterworth function, has a large number of derivatives vanishing at omega equal to 0, and therefore the function is called maximally flat. It cannot be more than this. The order of flatness cannot be more than twice n minus 1. Maximally flat at omega equal to 0. The next question is that of the asymptotic behavior of the Butterworth function. Asymptotic behavior, we know it passes through these 2 points, but how does it behave when omega goes to infinity? Let us see. HA of j omega magnitude is equal to 1 by 1 plus omega by omega c to the power 2n square root of this, if we take the magnitude, and therefore as omega goes to infinity, HA tends to omega by omega c to the power, yes, to the minus n, that is correct. When omega goes to infinity, it goes to omega by omega c to the power 2n, square root of that omega by omega c to the power n. If we take to the numerator, it becomes omega by omega c to the power minus n, and therefore if we take the log of this, that is, we want to express this in decibels, then you get 20 log 10 of HA. As the frequency goes to infinity, this goes to minus 20n log of omega by omega c to the base 10. Agreed? In other words, as omega increases by a factor of 10, the characteristic goes down by 20n. And what is 20n? It is expressed in decibels, and therefore the asymptotic slope is equal to minus 20n decibel. Decibel is written as small d capital B. Why capital B? Because B stands for a proper name and you must respect the name, not small b, okay? Small d capital B per decade. Omega increasing or decreasing by a factor of 10 means a decade, which is approximately equal to minus 6n decibel per octave. Actually per octave it should have been 6.0206. because log 2 is 0.30103, but for engineering purposes we take it as a round figure 6 cent. So, I said approximately equal to, but they are used interchangeably. It does not make much of a difference. Okay. 6 cent dB per octave. Octave is doubling or halving the frequency. Okay. So, this makes it clear that if we know the asymptotic slope, if you are required to design a Butterworth filter with 18 dB per octave asymptotic slope, then you know you require a third order filter, all right. But this is not what the specification, this is not the way to specify a Butterworth filter. As I said, specifications will always be in the form of delta P, delta S, omega P and omega S. This is how in practice a filter, a required filter is specified. So, we shall come back to this, but before that let us see if we know capital HA of j omega squared as 1 plus omega by omega c to the power 2n, this is not adequate for designing the filter. For designing the filter we require the transfer function HA of S. In the S plane we require the transfer function, and the process of analytic continuation says that HA of S, HA of minus S should be equal to 1 plus, you just replace omega by S by j, and therefore omega squared by minus S squared by omega c squared to the power n. All right. It is obvious that I can go from here to here by putting S equal to j omega, the result is okay. From here to here is possible only if the function is analytic, that is we are looking for an HA of S which has a finite number of singularities and the function is differentiable in the total S plane except at the singularities. That is the definition of an analytic function, and HA of S satisfies the conditions of analyticity. And therefore, what we require now is to find, you see there are two demanding transfer functions, one is HA of S, one is HA of minus S, and therefore we must find all the factors of this and assign half of them to HA of S and the other half to HA of minus S. The factors that we assign to HA of S must be such that their zeros are in the left half of the S plane, left half. In the Z plane they were inside the unit circle, in the S plane they must be in the left half for HA of S to become a stable transfer function, and therefore we must find all the roots and then make assignments. Well, the poles obviously satisfy minus S squared divided by omega c squared to the power n is equal to minus 1, right. At the poles the denominator should be equal to 0, and minus 1 you can write as e to the power j 2k minus 1 pi in general. Okay. E to the j pi is equal to minus 1, you can write it in this form, e to the j 2k minus 1 pi, and if I take n out from here, n out, then I can take pi by n. What will be the values of k? K will go from 1 to n, 1 to n, because now in this form we are finding the values of S squared, and the total function shall have twice n number of roots. If I find for S squared it would be n number of roots. So, k goes from 1 to n, not n minus 1. I am not starting from k equal to 0, I am starting from k equal to 1. Okay. So, my let me write it down minus S squared. Well, I can write this as S squared equal to minus omega c squared e to the power j 2k minus 1 pi divided by n. And if I take the square root of this, then s would be equal to plus minus j omega c minus 1 square root is plus minus j omega c e to the power j 2k minus 1 pi divided by twice n, okay, where k goes from 1 to, yes, n, because plus takes care of n roots, minus takes care of the other n roots. And it is now very easy to show that the plus sign corresponds to left half plane poles. Let us see how. The plus sign, we will call this as sk, okay. The kth root is given by this. Now if I take the plus sign, let us see what we get. Sk plus sign, sk is j omega c, I can write this as cosine of 2k minus 1 pi divided by 2n plus j sine of 2k minus 1 pi divided by 2n. And if I multiply by j, then I get omega c minus sine of 2k minus 1 pi divided by 2n plus j cosine of 2k minus 1 pi divided by 2n. All right. Now obviously one observation that can be made from here itself is that all poles are on a circle of radius omega c, because the magnitude of sk is equal to omega c. All right. Second, you look at the real part with the positive sign. The real part is at minus omega c sine of 2k minus 1 pi by 2n, and k goes from 1 to n. So if k goes from 1 to n, we start from pi by 2n and end up in 2n minus 1 pi divided by 2n, that is less than pi by an angle pi by 2n. So we remain in the upper semicircle, first and the second quadrants, and in the first and second quadrants sign is positive. Therefore the real part of sk with k equal to 1 to n is always negative, which means that these are the poles in the left half plane. So these are the poles in the left half plane, and these are our required poles, okay. Now let's see, let's take a few examples first. Sk, well, instead of writing omega c again and again, can I now write sk by omega c? Then I shall have minus sine 2k minus 1 pi divided by 2n plus j cosine of 2k minus 1 pi divided by 2n, k equal to 1 to n. Suppose I have the first order n equal to 1, then this is sine of n equal to 1 and k can only be 1. Then sine is 1, sine of pi by 2, and cosine of pi by 2 is 0, and therefore the root must be at minus omega c, and therefore HA of s, the transfer function, is simply s plus omega c. Not quite. Not quite. The numerator shall be omega c. You remember, for the transfer function the magnitude is 1 at omega, normalized to 1. In order to make it 1, we make it omega c, or we can write as 1 by s by omega c plus 1. Agreed? Take n equal to 2, then my sk s1 divided by omega c shall be equal to minus sine, put k equal to 1, pi by 4, right, 2 times 2 is 4, k equal to 1. So, 2 minus 1 is 1, pi by 4 minus 1 over root 2 plus j cosine of pi by 4 is also 1 over root 2. So, we get 1 over root 2, and if I know a pole is complex, its conjugate must be there, and we are only talking about second order transfer function. So, everything is found, minus half plus minus this, and therefore, H A of S shall be equal to S plus, let us write S by omega c, plus 1 by root 2 plus j 1 by root 2 multiplied by S by omega c plus 1 by root 2 minus j by root 2. Agreed? We have written the transfer function in terms of S by omega c, otherwise we will have to multiply this by omega c, okay, and the numerator we shall have to use omega c squared, and if you multiply this out, what you will get is omega c squared S squared plus root 2 omega c s plus 1, not 1, omega c squared. So, the second order Butterworth polynomial, the denominator of H A of S is called a Butterworth polynomial. Second order Butterworth polynomial is S squared plus root 2s plus 1 if omega c is 1, normalized to 1. Okay. Now, if we go to the third order, if we go to n equal to 3, where do you think, and let us normalize omega c to 1. It is convenient. Later on, if we require omega c not equal to 1, then we shall simply replace small s by small s divided by omega c. That is all the, okay. If omega c equal to 1 and n equal to 3, where would be the roots? Where would be the poles? Obviously, one is at minus 1 and the other two S 2 3 shall be equal to minus sine pi by 6 plus minus j cosine of pi by 6, that is at minus half plus minus j cosine 30 is root 3 by 2, and therefore H A of S omega c equal to 1 shall be equal to 1 over S plus 1 to take care of this pole. Then can I write this as S plus half whole squared plus 3 by 4, agreed? I have two factors, S plus half plus j root 3 by 2, and the other factor is S plus half minus j root 3 by 2. So, this is what it is, 1 by S plus 1, and this factor you can very easily see S squared plus S plus 1. So, the third order Butterworth polynomial has the two factors S plus 1 and S squared plus S plus 1. Okay. The we can also write this specifically as 1 over, if we multiply this out, S cubed plus 2s squared plus 2s plus 1. And if omega c is not equal to 1, then all that we have to modify is S cubed plus twice omega c s squared plus twice omega c squared s plus omega c whole cubed, and the numerator would be omega c whole cubed. That is, we have to replace small s by omega c. Now, this should convince you that if the order of the Butterworth filter is odd, then there must be a real pole at S equal to minus omega c. All other poles are complex. Just one real pole, all other poles are complex. On the other hand, if capital N is even, then all poles are complex conjugates. There are no real poles. Okay? In case the poles are complex conjugate, and let us say for simplicity omega c is equal to 1, then two complex poles shall give rise to a factor, shall give rise to a quadratic, right, what we did in the third order case, and the quadratic would be, quadratic polynomial would be s plus sine of 2k minus 1 pi divided by 2n, that is the real part, whole squared plus cosine squared 2k minus 1 pi divided by 2n. All right, S minus a complex pole S1, S minus S1 star would be this. Product of two complex pole, complex conjugate pole factors shall be like this, and this, as you can see, is S squared plus twice sine of 2k minus 1 pi divided by 2n S plus 1. Agreed? Cosine squared plus sine squared is equal to 1. And therefore, one need not even find the location of the poles. One may write, if one knows the order and omega c, one may write the transfer function directly. All that you have to compute is these factors, twice sine 2k minus 1 pi by 2n. Let us give a name to this, s squared plus bk s plus 1, where bk, the constant bk, is equal to twice sine 2k minus 1 pi divided by 2n. We must not lose sight of omega c, because omega c in all practical cases would not be 1 radian per second, it will be something else. It may be 500 pi radians or 1000 pi radians, depending on your cutoff frequency, 3 dB frequency. So, in general, therefore, H A of S would be of the form continued product of S squared plus bk. If omega c is not equal to 1, then bk shall be multiplied by omega c, bk omega c s plus omega c squared. K shall go from 1 to, if capital N is even, then k shall go from 1 to, pardon me, n by 2. Capital N is even, not n minus 1, n by 2, right? There should be capital N number of complex poles, and complex poles occur in conjugate pairs. One conjugate pair is taken care of by this factor. So, there are only capital N by 2 conjugate pairs. So, this is a continued product from k equal to 1 to n by 2, and the numerator shall be omega c to the power how much? N. Omega c to the power n. All right. On the other hand, if n is odd, then it shall be s plus omega c. There must be a pole at omega c, one real pole, and then continued product, the same factor, s squared plus bk omega cs plus omega c squared now k will go from 1 to n minus 1 by 2. The numerator shall still be omega c to the power n. This is n odd. You see how simple the design of Butterworth filter is. Once you know omega c, well, you must not lose sight of Bk. Bk is twice, do not forget this factor, twice sine of 2k minus 1 pi divided by 2n. All that you have to compute are these Bk's. Then you get the transfer function directly. You don't have to compute the poles. Only the sine factors, that's good enough. Let's take an example of capital N equal to 4, let's say, and omega c not equal to 1. Then we can directly write h a of s as omega c to the power 4 and two factors, s squared plus b1 omega c s plus omega c squared multiplied by s squared plus b2 omega cs plus omega c squared, where b1 shall be equal to twice sine of, yes, sine of pi by 8, right, and this comes out as 0.76537. If this filter is going to be used for design of IIR digital filter, then you better take care of these constants to as many decimal places as you can. Do not make truncations unnecessarily, because you shall end up in trouble. Quantization error adds further to the errors and may make the filter unacceptable. Okay? B2 shall be twice sine. You don't have to go back to 2k minus 1. If it is pi, the next increment would be by 2 pi, so 3 pi by 8. And this comes at 1.84776. So you know the total transfer function. If capital N is equal to 5, okay, and omega c is equal to 1, then you can write the transfer function directly as 1 divided by s plus 1 s squared plus b1 s plus 1 s squared plus b2s plus 1. I am going back and forth between omega c and 1 to familiarize you with the actual procedure. Now b1 is equal to twice sine, now pi by 10. Once you get some experience with this, you can even forget 2k minus 1 pi by 2n, okay, pi by 10, and this is equal to 0.61803, and b2 is twice sine, once again 3 pi by 10, and this comes at 1.17557. Now, how does one determine n? How does one determine the order? You see, the two things that are needed for Butterworth filter are omega c and n. Suppose omega c is given, suppose omega 3 dB frequency is given, you have to find the order. How do you do that? You look at the characteristic. What is the extreme end? Where does it go? Infinity. Unlike digital filters, in digital filters we stop at pi. Okay, so this is omega s, and this is delta s. Delta p, well, is not delta p. 1 minus delta p is 0.707. That is given. So if I write the transfer function, 1 by 1 plus omega s divided by omega c. Omega c is given. Omega c is the same as omega p. This is 1. This is 1 minus 1 over root 2. Omega c is given. No, I have made a mistake. It is 1 by root 2. Okay. So, this to the power 2n should be equal to delta s squared. Don't make a mistake. This is magnitude squared and this is magnitude. Well, that this is magnitude is obvious because I have written 1 by root 2, otherwise I would have written half. Don't make a mistake. These are the usual places where one makes a mistake. And therefore, I get omega s divided by omega c to the power 2n is equal to delta s to the power minus 2 minus 1. Agreed? If I take the reciprocal. So, capital N would be equal, if I take log of both sides, capital N would be half log 10 of 1 by delta s squared minus 1 divided by log 10 of omega s divided by omega c. Agreed? Okay. I have omitted one algebraic step. Take log of both sides, twice n log of this and then log of this. Okay. Now, there is no guarantee that this quantity on the right shall be an integer, whereas capital N we require an integer, right, and therefore you shall choose an integer which is higher than this but closest to this. If this comes out as 6.7, then you have to use 7. Do not go for 8 because that unnecessarily increases the cost of the filter. Okay. And when you choose capital N greater than this, so let me make it clear, capital N to be chosen is greater than or equal to this. If capital N is greater than this, then obviously the actual omega s that you shall realize will be somewhere here. In other words, the stop band is pushed to the left, and what you wanted, the attenuation at omega s, now shall be less than delta s, which is a welcome feature, but you must not play with the stop band. Stop band is sacred, cannot be touched. Okay. Now, this is a fortunate situation where omega c, pass band is sacred. Okay. Pass band is sacred, you must not touch the pass band. All you can do is to play with the stop band. Now, this is a situation where omega c was specified. In general, omega c shall not be specified. What shall be specified is 1 delta p let us call this delta p. Okay. This is omega p. Delta p is not the tolerance in the pass band. If you want, I will use some other symbol, but tolerance in the pass band is now 1 minus delta p. Okay. Then this is delta s. To keep the formula simple, this is delta s and this is omega s. So, how do you determine? Now, you have to determine two things, omega c and capital N. This is arbitrary. The tolerance can be 1 dB, for example. If it is 3 dB, then you know delta p is 0.707 and omega p is the same as omega s, omega c. But if this is the general specification, then you write the two conditions, that is 1 plus omega by omega c to the power 2n omega p, this is equal to delta p squared, right, and 1 by 1 plus omega s divided by omega c to the power 2n is equal to delta S squared. All right, clear? If I take the reciprocal of this, and subtract 1 from it, then I shall get delta S minus 2 minus 1. In a similar manner, omega p by omega c to the power 2n shall be delta p to the minus 2 minus 1. And now we take the ratio, that is omega s divided by omega p to the power 2n is equal to delta s to the minus 2 minus 1 divided by delta p to the minus 2 minus 1, and therefore capital N shall be half log 10 of delta s to the minus 2 minus 1 delta p to the minus 2 minus 1 divided by log 10 of omega s divided by omega p. This is the general formula for determining the order of the Butterworth filter, and in order to emphasize that capital N may or may not be an integer, this right hand side may or may not be an integer, n should be greater than or equal to this. Okay? So once you obtain capital N, the next step is to obtain omega c, and there are two equations which compete with each other. These are the two equations for determining omega c. Which one should we use? The first one, because the passband is sacred. I must satisfy the passband tolerance exactly. I can over satisfy the stop band tolerance. Okay? So capital N, whatever value you have obtained, you substitute this in 1 by 1 plus omega p divided by omega c to the power 2n is equal to delta p squared. From this you find omega c. Then omega s, that is actually obtained, realized, if n is greater than that quantity, half of ratio of 2 logs, then omega s prime shall be less than omega s. In other words, you are bringing the stop band in the transition band, and that is a welcome feature. Where you required 40 decibels, if you get 60 attenuation, you are happy. Now that brings in the question, delta p and delta s are usually specified in decibels. If they are specified in decibels, then you have to convert them into ratio. Suppose delta p corresponds to AP decibels and delta s corresponds to AS in decibel. Then 20 log 10 delta p is equal to minus AP. That is correct. Minus AP, because 1 corresponds to 0 decibel. Anything below that must be negative. Okay? And therefore delta p is equal to 10 to the power minus AP by 20. In a similar manner, delta S equal to 10 to the power minus AS by 20. So you shall have to convert the decibel specifications into ratio, that is pure numbers, and then find out capital N.